Hey guys, so we're going to go over Q3 on discussion 9 exam level worksheet. This is an algorithm design problem, so it's very word heavy. We're going to break down every part of the problem and break down the concepts that it's trying to teach us. And hopefully by the end of this, you'll know how to design an algorithm. So let's get right into it. Two countries, Mondstadt and Fontaine, are located in the fictional world of Teyvat. The railroad system of Teyvat can be modeled as a weighted directed graph, with V vertices, E edges, and weights being the length of the railway. Circle the traveler wishes to take railway from Mondstadt to Fontaine and needs to determine the shortest railway distance between them. Define the set M to be all cities in Mondstadt and F to be all cities in Fontaine. The shortest distance between the two countries is the shortest distance between any city C of M in Mondstadt and C of F in Fontaine. For each subpart below, describe an algorithm that computes the minimum railway distance from Mondstadt to Fontaine in O V plus E log of V time. You are able to call all graph algorithms you learned in class as a black box. Hint, for some parts, consider modifying the graph so that running a graph algorithm yields an equivalent answer to solving the original problem. So let's break down what the problem is giving us. So first of all, we have a weighted directed graph. So all edges are going to have a specific weight, and these weights are going to be the length of the railway system. We also have V vertices, E edges. And we want to find the shortest distance from Mondstadt to Fontaine, and we want to make sure it equals to that runtime. So let's get right into it. The first problem is saying Mondstadt only contains one city and Fontaine contains many cities. So when it comes to problems like these, I always like to draw a graph to visualize it. So let's do that. So we have one city in Mondstadt, and we have multiple cities in Fontaine, right? And these are connected in some way, and they have X amounts of weights. You don't really need to know like exactly the weights, it's just more like conceptually. So looking at this, because we want to find the shortest distance from Mondstadt to any city in Fontaine, we can just run Dijkstra's. The trick about this is we start at M and we iterate through all cities in Fontaine. And in doing so, this is going to give us the minimum distance from that one city in Mondstadt to any of these one cities in Fontaine. The next problem is asking where we have Mondstadt contains many cities, but Fontaine only contains one city. So this is basically flipped from the original one. So we have many cities in Mondstadt, and we have one city in Fontaine, and these are connected, let's say like that. The trick of this is because we want to find the distance from M to F, we can't start at that one city in Fontaine and iterate through everything in Mondstadt like we did for part A. We also don't have a starting vertex like we did in the previous one, because Mondstadt was only one city. Because technically, any of these cities could be the starting point to the fastest route. So this is where the hint comes in that they gave us in the question. So it's saying, consider modifying the graph where when we run the algorithm, it gives us an equivalent answer. So if we want an equivalent answer and we want to modify the graph, the best way to do this is to create something that we call a dummy node. So let's say we have this dummy node. And because we want to start at Mondstadt, we're going to connect this dummy node to all potential vertices in Mondstadt. The way we make this equivalent to solving the original problem, because technically we're creating like a new graph because we're adding this dummy node, we're going to set the weight of all these edges to 0. What this basically does, starting with the dummy node, it's going to iterate through all cities in M. And with that weight 0, it's basically creating a new graph G prime. So we could basically run Dijkstra's starting from the dummy vertex D and take the distance from D to the only city in F and return it. So it could iterate like this, and then it's going to iterate like that, or it could start from here, or it could start like that, or it could start like that. So it's basically going to, the way this works is because for each path in the original graph from any city in M to F, it corresponds to a path in the new graph of this like G prime that starts from D and ends in that singular city in Fontaine. And because the original weight we set to all of these edges are 0, it doesn't add any like edge to that railway from one city to the other. So therefore, our algorithm can correctly compute the shortest path from any city, any starting point city in M, to that singular city in Fontaine. Lastly, it's saying both countries contain many cities. So once again, we are going to draw this out. So we have all of these in M. And now we have, let's just put 2 in F. And these are all connected in some way, shape, or form. Once again, we don't really have a starting vertex in M, so we're going to do the same process we did in part B, where we create a dummy node. That's going to go to all of the indexes, all the vertices in M. We're going to set all of these edges to 0. The only difference this has from the previous part is we're not ending at M, that at one singular city in F. We're also adding another city in F, or adding multiple more cities in F. So this creates a dummy vertex D. For each city in ModStat, we create an edge from D to that city with edge weight 0. This once again creates that new like G prime graph that we talked about. And we can once again run Dijkstra's starting from dummy vertex D. Now, instead of directly taking the graph from D to the only city in F, we take the minimum difference from D to all cities of F, and we return it. I hope that makes sense. I hope these visualizations helped, and I hope this helps you understand the algorithm design aspect.